the class keeps thinning out. By the end of April, I'm going to be talking to an empty classroom, actually to my TAs. So I have the strong suspicion that by the time the second homework is done, the registration in the class is going to be really down. Lots of people seem to be having trouble with homework 2, which I don't quite get. It's actually easier than homework 1. So are we good to go? Yeah. Okay. Morning, everyone. By the way, so there's a really nice talk tomorrow morning at 10 a.m. by faculty candidate Pulkit Agarwal. He works on alternatives to reinforcement learning, what he calls learning by exploration, and it's a lot of really nice work using neural networks. But how he formulates it is really cool, and he has this entire new paradigm. So if you guys get a chance, you should check it out. That's worth your time. So we're going to be continuing with the talk on recurrent neural networks today and on Wednesday. Here's where we are. We started off with saying that recurrent neural networks are really good at doing all kinds of interesting things, like literally synthesizing, generating this program. There was a recurrent neural network which learned how to produce text, or this mathematical, very official looking text which has been produced. Now imagine if there were any actual intelligence behind this actually writing out math. That would be impressive, but it seems to be able to fake it, right? Or even fake text. So these things are immensely powerful, and and what we did in the last class is to get some initial ideas of what the basic formalism itself is. We are going to continue along the same lines. We'll look at some issues of how these work, some ideas of what could possibly go wrong and how things are fixed, and variants, which are LSTMs. In the next class, we will look at the issue of how you can actually pose the loss function, the divergence for these networks to really make them work. Now, so the story so far, we saw that iterated structures are good for analyzing time series data with short time dependency on the past. So these are time delay neural networks or convolutional neural networks. It's convolutional if you're actually looking across all dimensions. If you're looking only across time, if you're looking at time series data, these are just time delay neural networks. Now, we saw that recurrent structures are good for analyzing time series data with long-term dependencies in the past. Iterated structures are good for looking at the past n instance, where n might be a relatively small number. But if you want to look back 100-time instance or 200-time instance, then you really want to be looking at recurrent networks. So where you have some information that is passed on over time, which is retained and passed on over time. So these are what we call recurrent neural networks. We saw a few different formalisms: Knox networks, Jordan networks, and Elman networks, which explicitly try to retain a little unit that stored memory, and then finally what we call fully recurrent networks, which are networks of this kind. Now, here's where we stopped. I claimed that recurrent networks can do what static structures cannot. So here is a simple problem. I would like to add two numbers. I want to train a multi-layer perceptron, build a multi-layer perceptron to add two binary numbers, right? So I have the inputs are two binary sequences. The output must be the sum of the two. The output is obviously going to have one more bit than the inputs. Now, Can you tell me what kind of network would do this? Can somebody give me an idea of how you would go about designing an MLP for this task? Anyone? You should be able to hand draw it. You know, it's very deterministic, yes. So it's not stochastic, you're not going to be learning it anyway, yes.
So the first layer is like the last 2 digits. And then it has 2 outputs. One is the value at this unit, and one is 2 before. And then the second layer is to handle 3 digits, which is the second last digits, and what is from the last layer.
So basically, if you want to do it in a straightforward multi-layer perceptron, you're really not going to be able to do it because this is a classic XOR problem. Addition is XOR, right? If you want to do XOR, you're really going to require an exponential number of units in the first hidden layer if you want to do it, or if you want to do it with just one hidden layer. If you want to make it deep, provided you're willing to also pass on input directly to later layers, as you point out. What's your name, by the way? I didn't get that one. So like what he said, if you're willing to say, the first layer is going to work on the first bit, and you can pass on the input and the output of the first layer to the second layer, you can make it in a linear number of with a linear number of units. But if you're not passing input on downstream, if you're not making this network deep, it's going to be incredibly large. But in addition to size, now even if I have managed to build a network to add 2 n-bit numbers, if I want to add an n plus 1 bit to n plus 1 bit numbers, this thing's going to fail, right? Let's do this with a recurrent network. That's your recurrent network, right? 1 bit. It's really, really tiny. So all it's going to do is to take the recurrent network is going to have literally just 3 neurons in it, which is the classic XOR. The first input, at each time it's going to be taking the 2 inputs and the carryover. So it's going to be 5 neurons. And you can just pass the entire data through sequentially, and you're going to get the sum of 2 numbers. So here's a problem where when I wanted to do something using a standard multi-layer perceptron, I ended up with very large complicated networks. But if I want to replace that with this MLP with a recurrent network which just passes over the data, it's able to do the job much, much more efficiently, right? So here's another problem, the parity problem. How many bits do I have? Is the number of bits in this input sequence even or odd? Again, if you want to do this with an MLP, you need an exponentially sized MLP, because this again is an XOR, right? Or you're going to need many, many layers, and the network gets fairly complex. But then if I want to do this using a recurrent network, that's it. You're going to have one input, and then you're just going to keep carrying over the output after having processed the previous input bit. So if you've got an even number, the next time you encounter a 1, it's going to become a 0, and then the next time you encounter a 1, it's going to become a 1. It's just a simple, tiny little network which can scan the input and give you the parity, right? So what we are saying is that recurrent networks are not merely little tools meant for time series data. Even for other more conventional problems, if you're willing to think of it as scanning the input and producing an output, these can give you very efficient structures, right? So recurrent networks are actually more versatile than MLPs, even on problems that seem on the surface to be appropriate for MLPs and not recurrent networks, right? Now, we also saw that the recurrent net structures can be trained by minimizing the divergence between the sequence of outputs and the sequence of desired outputs. So you're not really minimizing the divergence at individual times. You're interested in how does this entire sequence of outputs produced by the network compare to the entire sequence of outputs that I would really like the network to produce. And we will discuss this a little more in the next class. And we can actually we train the network by back propagating the error between what we want the output to be and what the output really is through the network. We can have different kinds of recursion. So you could be recursing just to one time step in the past, or you could be looking back 2 time steps. You could be looking back 3 time steps. You could be looking back any amount of time. So there's nothing magical about the one step forward recursion. Once you decide that you're actually going to recurse, and you're going to look back and use the network's own outputs or intermediate values from the past, you can go back any amount of depth into the past, right? Now, how does this entire system actually behave? What kind of generic behavior would you expect to see from a network of this kind? Let's return to our old model. Let's say the network only depends on some fixed window of inputs. So to produce the output at any time t, you're looking at our input at time t, t minus 1, t minus 2, and t minus 3. Would you expect this network to ever blow up? What I mean by blow up is the network value just goes into the sky, becomes infinite, or if you've got if it's built of saturating units, it just saturates and doesn't do anything more further, right? Would you ever actually expect a network of this kind to blow up in this manner? Either go off to infinity or saturate and produce effectively meaningless results. So would you? Anyone? Under what conditions?
Well, I can really kind of relate it back to the Riemann modeling standards. If your process isn't following a stochastic path, for example, it can grow unboundedly, or you can kind of.
This is MA. So you have something called Bibo stability, which means bounded input, bounded output. Anybody who has done signal processing recognizes this, right? This is a finite impulse response system. If it were linear, if you're an electrical engineer, finite impulse response systems, can they be unstable? They cannot, right? But so time delay structures have bounded output if the function f has bounded output for bounded input, which is true for almost every activation function, and the inputs themselves are bounded. So this is what is called a BIBO, or bounded input, bounded output stability, and it's highly desirable. You don't want your network to just blow up. You're working along, you're giving it inputs, at some point it hits the roof and then never comes back. That's not acceptable behavior, right? And that will not happen if you have things which look only at the inputs, right? Now, something like this, is this going to be bounded input, bounded output? Yes. Actually, you're right, right? So anyone else? That's exactly the answer, right? Now this is guaranteed. Boundedness is guaranteed if the output activations have a ceiling, but boundedness by itself is not useful. We're more interested in, will it saturate? Will it just hit the ceiling and not do anything further, right? So and do you lose information? Now instead of looking at will it saturate, it makes more sense to look at boundedness, because saturation is a function of things going off into the roof, right? So let's consider this situation where all the activations are linear. When all the activations are linear, then in order to analyze the behavior of this network, it's sufficient to analyze the behavior of the hidden layer HK, because the HK is the layer that actually carries the relevant information into the future. That's where all the information is going through, right? And for simplicity, I'm going to assume that there's just one hidden layer. But if you have multiple hidden layers, the same behavior is going to replicate. It gets a little more complex, right? And like in the past, we're going to use the streetlight effect. We will analyze things that we know how to analyze and hope that whatever analysis we have carries over to things that are more complex. So we'll look where we know how to look, regardless of whether the answer is there or not. And specifically, we're going to look at linear systems. Now, here, every neuron I'm going to assume is a linear function. So the hidden layer, the inputs to the hidden layer are the weighted sum, is a sum of a weighted combination of the output of the hidden layer at the previous time and the inputs at the current time. And the output of the hidden layer is just the input itself, because the activation is just linear. We are assuming no non-linearity for the moment. So here's how the system is going to behave, right? At the current time, hk is going to be some wh times hk minus 1 plus wx times xk, which is a weighted sum of the hidden layer at the previous time plus a weighted sum of the input at the current time. But then if I take a step back, hk minus 1 itself is wh times hk minus 2 plus wx times xk minus 1. In other words, the output of the hidden layer at the previous time was in turn a weighted combination of the hidden layer at the previous time and the inputs at the past time, right? So putting those two together, here's what the output of the hidden layer at time k looks like as a function of the hidden layer output 2 time instance in the past and the past 2 inputs, right? Now observe that this is as you keep going back, now it's a function of wh squared, right? I can take this one step back. It's going to be a function of wh cube. If I work it all the way back to whatever the beginning of time, this is going to be wh raised to k plus 1 times the very first, the initial value of h plus lower powers of wh that operate on a weighted combination of the inputs, right? Now this is just a nice series, and something interesting that falls out of the whole process. What is this first term over here? This first term over here is what the output of the network would be, or the hidden layer value would be at time k if there were no input at all to the system, right? So this because all of the remaining xk's are 0. The second term over here, similarly, is what the output of the system would be at time k if you had no initial value and all subsequent outputs were 0. The whole thing is linear, right? Similarly, this third term is what the output of the network would be at time k if the input at 0 was 0 and there was no initial value and all subsequent inputs were also 0. So basically what we are finding is that the output at time k is going to be the output of the network, or is going to be a sum of the output of the network to the initial value and only the initial value plus the output of the network in response to an input at time 0 and nothing else, plus the input at time 1 and nothing else, and so on. And furthermore, because the system is linear, in fact hk of x is simply going to be x times hk of 1, right? Because x is simply a vector that's multiplying the inputs. So assuming that the inputs are scalar for now. So I'm just speaking of scalar systems over here. So considering this, it turns out that the output at time k can really be looked at as the sum of outputs in response to a single input shifted in time, right? So this is what you'd get if you had an input at time 0 and nothing else. This is what you'd get if you had an input at time 1 and nothing else. This is what you'd get if you had an input at time 2 and nothing else. So given this, I can analyze the overall behavior of hk if I analyze any one of these guys, because all of these are just basically scaled variants of the same fundamental pattern, right? And so what this means, it's sufficient to analyze the response to a single input at time t equals 0. If it blows up in response to time t, a single input at time t equals 0, it's going to blow up in response to a single input at time t equals 1, and so on. So and if it doesn't blow up in response to this, it's probably not going to blow up simply because you have more inputs. So let's look at how this single behavior, and this is a principle of superposition in linear systems. That's basically what we are looking at, right? This is because I got rid of the nonlinearity in the system. A linear system can be decomposed as the sum of the responses to individual inputs in a time series. Now consider a simple scalar linear recursion. And so h of t is going to be w times h of t minus 1 plus c times xt. So this is just scalar, right? So what will happen if I have an input? So h0 of t is my notation for the response of the system to an input at time 0 and nothing else. If all I have is an input at time 0 and nothing else, then the output of the system at time t is going to be w raised to t times c times x0. We can just work our way through the recursion, right? Now look at what happens if I let the system just evolve over time. Now this system is basically, x of 0 is just a constant, c is a constant, the behavior is simply w raised to t, right? Which means that it's going to either, depending on the value of w, it's either going to fall quickly to 0, or it's going to sort of fall slowly to 0, or it's going to blow up. So if w is 1, the output is going to remain constant. If w is even marginally less than 1, it's going to fall off. The smaller w is, the faster it's going to fall off. If w is greater than 1, it's going to blow up. Now you really don't want the system to blow up. So w greater than 1 is not a great idea over here, right? Now suppose I think of this in terms of a vector. See, this is just a simple scalar input. I have inputs as scalars, and I'm looking at scalar operations. Now let me look at it as a vector. Now h of t is w times h of t minus 1 plus c times xt. C is a matrix, w is a matrix, h is a vector, x is a vector. That's just again the linear system that we just looked at. So if I assume that h of minus 1 is 0 for now, okay? And it doesn't really affect the analysis, so I can make that assumption. And all I have is an input at time 0. So it's an input vector at time 0, x of 0. Once again, what is the output of the system going to be at time t? It's going to be w raised to t times c times x, where w is the matrix, right? So it's a matrix raised to power t times whatever input. Now the behavior of this also is entirely governed by w, right? Now regardless of the matrix, so here I'm assuming w is a square matrix, and it has to be because I'm multiplying an h and getting back something that's the dimension of h. Because it's a square matrix, I can use eigen decomposition and write w equals u times lambda times u inverse, right? And so w has some eigenvectors. The property of an eigenvector is going to be w times u is lambda times u, where lambda is the eigenvalue corresponding to the eigenvector. Now the eigenvectors are all going to be independent of one another, which means that the eigenvectors span the space, which means any vector h can be expressed as a linear combination of the eigenvectors because the eigenvectors span the space, right? What happens when I multiply wh? H by w. Wh is going to be w times a1 times u1 plus w times a2 times u2 and so on. But what is w times u? U is an eigenvector, right? So w times u is just lambda u. So this is going to be a1 times lambda 1 times u1 plus a2 times lambda 2 times u2, so on, an times lambda n times un, right? N is the dimensionality of w. If I multiply this by w, what happens? This is going to be a1 times lambda 1 times w times u1 plus a2 times lambda 2 times w times u2 and so on. But again, w times u is simply lambda u, right? So that would become a1 times lambda 1 squared times u1 and so on. So in general, if I multiply this by w raised to t, this is simply going to be a1 times lambda 1 raised to t times u1 plus a2 times lambda 2 raised to t times u2 all the way to the nth eigenvector. Now this is very straightforward. This is a standard, Lang's expansion, right? We use these iterations to actually come up with, identify principal eigenvectors and so on. But anyway, so in the limit as t tends to infinity, what will happen? If I have even a small difference in the eigenvalues between in the eigenvalues, because we are exponentiating the eigenvalues, eventually only the largest eigenvalue is going to remain. All the rest of them are going to become vanishingly small in comparison to the largest eigenvalue. So in the limit as t tends to infinity, w raised to th is simply going to be this term, which is just the contribution of the largest eigenvalue, right? The eigenvector corresponding to the largest eigenvalue, all very fine. So for any input for large T, the length of the hidden vector will expand or contract according to the tth power of the largest eigenvalue of the hidden layer weight matrix. So all you really need to know is, what is the largest eigenvalue of this weight matrix of the hidden weight matrix that connects the hidden layer, and the output of the layer in response to a single input is either going to grow or it's going to fall based on the value of this largest eigenvalue. And if the current value, well, that's not always going to be the case. If the current value of h does not have a component along this largest along the eigenvector corresponding to the largest eigenvalue, then it's going to grow according to the second largest eigenvalue. If it doesn't have components along the first two eigenvectors, then it's going to grow according to the third largest eigenvalue and so on. But those are special cases. In general, we can just focus on the largest eigenvalue, and depending on this guy, you will know whether the system is going to blow up or whether the system is going to blow down. You're going to collapse, right? This is just, you just have to look at the eigenvalues of the weights matrix. So if the real value, again, eigenvalues can be real or complex, right? So if the real value of the real component of the largest eigenvalue is greater than 1, then clearly this is just going to keep growing and growing and growing. If it's smaller than 1, it's going to keep falling, right? And so if you have at middling values of t, this is what happens as you go across time, as time keeps incrementing. But you don't have to go very far. Even at intermediate values of t, you're going to get the behavior is going to depend on these eigenvalues, except that if you're not at the limit, if you're somewhere in between, the remaining eigenvalues will also factor in and complicate the response a little bit. So here are some standard behaviors. Here, this is a vector recursion. I have started with some h and applied the standard recursion over here. That's for the specific h that I've used. This is a 4-dimensional system, and the input is 1 at all for the hidden values in all 4 components. And this is what happens when lambda max is 0.9. This is, wait, what is the red? Oh, there are 2 components, okay. So this is what happens when lambda max is 0.9. This is what happens when lambda max is 1. Lambda max is 1.1. And the same thing. I have 3 different plots over here. Now the 3 plots have something different over here. These 2 correspond to complex eigenvalues. This complex corresponds to real eigenvalues. And you can see that when I have real eigenvalues in the last case, if the largest eigenvalue is just 1, the system quickly settles to the direction of the eigenvector corresponding to the largest eigenvalue and just stays there, right? If the largest eigenvalue is even slightly greater than 1, the thing just blows up. Now we are looking at the magnitude of the h vector itself. And here, if the eigenvalues are complex, it's not going to be nice and monotonic, it's going to oscillate. And here the largest eigenvalue is 0.9, and I have 2 different cases. In the blue case, the second largest eigenvalue is 0.5. In the red case, the second largest eigenvalue is 0.1. And you see, instead of things being nice and monotonic, it sort of oscillates because it's complex, but it's still going to behave pretty much exactly in the same way, in that because this is less than 1, the thing is going to taper off, right? Here, this is still complex, but then here, the largest eigenvalue is 1. After some time, it just falls into a nice oscillatory pattern. It's a sinusoid, but it stays flat, right? And if it's greater than 1, the thing blows up. So the behaviors that we are seeing over here is, in linear systems, long-term behavior depends entirely on the eigenvalues of the hidden layer weights matrix. If the largest eigenvalue is greater than 1, the system is going to blow up. And if it's less than 1, the response will vanish. It just falls off and it's going to disappear very quickly. Complex eigenvalues are going to make the system oscillate a bit, which may or may not be what we want, right? And if you want smooth behavior, then you have to force the eigenvalues to be real. One way to do it is just to ensure that your weights matrix is symmetric, but that's not something that you necessarily want, right? Now, so we see how this thing behaves with linear activations. Now, this affects what we expect from the system. So assuming that in the hidden layer we use only linear activation, something that we actually will do later on, right? These are the kinds of behaviors you can expect. Now, do you really want the hidden layer to keep growing and blow up? You really don't, because if the hidden layer output becomes, very large, whatever it feeds to is going to saturate one way or the other, right? On the other hand, you don't want it to vanish and become 0. So ideally, the hidden layer must remember stuff, but not forever. So you want some behavior where as time passes, it keeps forgetting, but it doesn't forget instantaneously, and the memory doesn't go, explode. Now, this is just with linear activations. Now, if I introduce some non-linearities, what happens? This is exactly the same system. In this case, here I'm actually looking at scalar values, right? So for scalar values, for different weight values, which are indicated by the color, I am using 3 activations. So in the case of nonlinear systems, h of t is going to be some activation applied to the weighted combination of inputs, right? And here's what happens if my activation is a sigmoid. Observe something very interesting. It does not matter whether the weight is greater than 1 or lesser than 1. The thing very quickly saturates and then stays constant. It really has no memory at all, right? Regardless of the weight. This was a question somebody even posted on Piazza. Why do I use tan H's in the hidden layer? So what happens when you have a sigmoid? This is the behavior. If in this case, when what happens if I have something like a ReLU? It blows up. The moment you have a weight that's greater than 1, the thing just blows up. If it's less than 1, it tapers off really quickly. In between, you have a tan H, and in the tan H, you can see some interesting behaviors. Tan H actually, if the weights are too large, it saturates at some value, but it tends to fall off much more slowly than the other two. And why does this happen? It's very easy to intuit. Now, in both of these cases, the outputs are strictly positive. So you get a behavior which is very akin to what we see when we have Hebbian learning. Things just keep accumulating. And if things keep accumulating, they're going to saturate at some value or they're going to blow up, right? Now, whereas if you have something like a tan H, which has both positive and negative outputs, both polarities, then you have a much, the behavior is, you expect the behavior to be much more, well, not stable, but the kind of behavior you really wanted to have, namely that you wanted to remember stuff, but not forever. And that's basically what you see over here, that it tends to remember things. Sometimes for some values of W, the memory fades really quickly, but it doesn't really blow up. So now, here, this was with scalars. Now, here the initial value of x was 1. Here, I start off with a negative start, where the initial value of the hidden layer is -1, and you get the same behavior, right? It's going to saturate at the same value. If it's a sigmoid, it's saturating once again very quickly. If you have a ReLU, if the initial value is negative, it's never actually, the weights are positive, it's going to stay 0. Nothing really happens. A ReLU is a horrible thing to be having. There is no memory whatsoever. If the initial value is negative, there's nothing to be remembered, in the directions where the weights are also positive. But again, in the case of a tan H, you get the kinds of memory behaviors that you expect, or you know are indicative of something actually being remembered. Now that was for scalars. What happens if I actually go up to vectors? Things get a little more complex. So here I have an initial value of all ones, or a scaled version of all ones, so that the vector length itself is just 1, yes?
Can you go back a sec? If you have like leaky ReLU for negative starts, would you also get, because it is linear but not,
You're going to get something like the linear behavior once again, right? So what you would not see is something like that, but nevertheless it is linear, right? Anytime it's linear, or any combination of linear which is unbounded, things can blow up. Now this was for vector inputs. I'm showing you the length of the hidden value vector, hidden vector, and again with sigmoids you see what happens. Saturates. For your ReLUs or equivalent, something that's somewhat linear, things blow up, right? And with tan H's, the behavior is a little more complex, but then things tend to be a bit remembered, and you can actually work this out. The arithmetic is fairly straightforward, but the behaviors here are completely explained by the fact that the output of any layers after any even a single step is strictly positive, right? And then after that you're just going to keep building things up on top of positive numbers. And here's the same thing when I start at a different point, which is the exact opposite. All components are proportional to -1. And again, you see the same behavior. The sigmoid saturates, the ReLUs blow up. The tan H has some a more reasonable memory behavior. So you get an idea, right? One of the things you do have to worry about when you have recurrent structures is what will happen. Recurrent structures don't come free. Things have, when things self-refer, they have the unfortunate tendency to either die off really quickly or to blow up, and neither of these are really behaviors that you want in general. So whatever appropriate function that whatever activations, whatever design you have for the network must be of the kind that can actually support memory behaviors. But then these are very prone to instability. Making these things actually work is a really tough task, and the typical range of settings, weights and such like, where they give you appropriate behaviors can be quite narrow. Now if we haven't actually looked at formal stability analysis, for linear systems you can actually perform formal stability analysis. You can look at Routh-Hurwitz criterion and so on. For nonlinear systems you have to look at basically Lyapunov functions, which look at stability in the vicinity of where they converge, and things like that. But the behavior conclusions that you will get in general are going to be similar, that of the activations that I actually saw, tan H's are the only ones that give you any reasonable memory behavior. And even these have very short memory, as we just saw. Bipolar activations are what you really want. They are nevertheless sensitive to the eigenvalues of the weights matrix, and the best case memory is short. And you generally have exponential memory behavior. Things are going to be either grow exponentially or they're going to be forgotten exponentially fast, right? So it's not a catch-all. It doesn't solve everything. But that was with only one tap. What happens if I give you 2 taps? So say instead of looking 1 step in the past, suppose I say I look at 1 step in the past and then I again look at 2 steps in the past. Now we're going to get more complex behaviors. So if I have a response at the current time, you can expect it to reflect in the next time instant and the next time instant if I'm only looking at 1 time step in the past. If I'm looking at 2 time steps in the past, if I have an input now, that's not going to show up, it's not going to reflect in the output of the next instant. It's going to reflect at the output 2 time instants from now, and then again 2 more time instants from there, and then 2 more time instants from there. So you're going to get the behaviors that we saw, but with a gap, right? So what if I have 2 taps? If I look back 1 time instant and 2 time instants, then you're going to get more complex modal behaviors, right? So in general, as you add the number of taps, if you have something like this, say t minus 1 and t minus 5, you'll observe that or with different weights, you're going to get these interesting looking peaks in response, and the positions of the peaks are going to depend on multiple things: on the tap value itself. So you can expect peaks at a lag of 1. You can expect a peak at a lag of 5, but you can also expect peaks at a lag of 4, right? Because 5 plus or minus 1, and a peak at a lag of 6. So as you add more and more taps, you are going to get more and more complex behaviors in what is remembered, instead of getting this nice smooth exponential roll off one way or the other, and things become more complex. Regardless, the point is that the behaviors are kind of unpredictable, and they have the tendency to not exactly do things the way you want them, you would expect them to behave. Now, generally, we sort of only look at a lag of 1, right? But ideally, if I want to be looking at something that's that far apart, I must choose a lag that far out, because I know that if I use only a lag of 1, by the time it gets this far out, everything is going to be forgotten. And you will, in generic situations, you won't know how distant that lag must be, because you don't really know the characteristics of your data. Anyway, moving on. So the kinds of analysis we saw, we can actually do this for vector functions with nonlinear activations. For linear systems, we're going to use Routh's criterion again. Nonlinear systems, Lyapunov functions. The general conclusions that we saw are not going to change. It's that which are this, that excellent, although RNNs are excellent models for time series analysis, like prediction, classification, sequence prediction, and they can even simplify problems that are difficult for MLPs. The manner in which they deal with memory is not straightforward, and it's not something that you can just treat as a black box and it's just magically going to work. There are behaviors which might, the ability of these things to remember depends critically on the weights, and they have a tendency to either blow up or forget really, really quickly, right? Now, here's another problem. This is a term that you might actually encounter, the vanishing gradient problem, which is a particular problem with training deep neural networks, which has to do with the gradient of the error with respect to weights. And this tends to be unstable. Now, remember, when we are doing a gradient descent, when we are training via gradient descent, the question we ask at each point is that how much will the error change if I change this particular weight or this parameter a little bit? And if increasing it is going to decrease the error, you will increase the weight. If decreasing it is going to decrease the error, you will decrease the weight. Basically, at each point, you're looking at how the error is going to change with a small change of the parameter, and you're going to shift the parameter in the direction that's going to reduce the error, right? That means we need to be able to compute these derivatives. How much will the error change if I vary this guy a little bit? Now, here is a simplified way of characterizing a multi-layer perceptron. A multi-layer perceptron is actually just a nested function, right? You have the outermost activation operating on a weighted combination of the outputs of the previous layer, which in turn is an activation operating on a weighted combination of the outputs of the layer prior to that, and so on, all the way until the innermost function just operates on a weighted combination of the inputs. So you have a function operating on a function, operating on a function, operating on a function. A multi-layer perceptron is just a nested function. It's a vector function, right? So here, these W's are the weights matrix at the kth layer. Now, the error for any x is going to be, which I'm just representing as divergence as a function of x over here, is the divergence between the output of the network and some desired value, which I have not explicitly represented, right? Now, here's the standard vector derivative chain rule. Now, on top, I've written it as dy over dx, just for illustration. But in terms of when we are speaking of vectors, you never write things that way in real notation. But this is meant only for illustration. So if I have some function which operates on w times g of x, and I want to find the derivative with respect to x, that's going to be the derivative of the function with respect to w times g of x times the derivative of w times g of x with respect to g of x times the derivative of g of x with respect to x itself. Just the standard chain rule, right? So if I let z equals w times g of x, this first term is simply the gradient of f with respect to z. The second term is the gradient of z with respect to g of x, which is just w. And the last one is the derivative of g with respect to x. So this is standard chain rule, right? Now I'm calling these gradients, this is really the Jacobian. So this is a, yeah. Okay, we just saw that you get, we've seen this chain rule in the past, right? So let's go back and look at what happens when we take the derivative of the divergence of between the actual output of the network and the desired output with respect to the output of some kth layer, fk. So that's going to be the derivative of the gradient of the divergence with respect to fk, which is the gradient of the divergence with respect to the argument to d, right, times the derivative of fn with respect to its argument times the weights matrix times the derivative of the next fn, or this fn minus 1 with respect to its argument, times the next weight matrix, and so on. I've just written this whole thing out using the standard chain rule that we just saw. Now we've seen this several times in the past. So when I've written the derivative of fn, I'm actually, this is the Jacobian. I'm just using a standard notation so the whole thing looks kind of uniform. Now all of the blue terms over here are matrices, right? The red term is a vector. The red term is a row vector, the way in our notation. So the first red term is a row vector, and subsequently the chain rule keeps tagging on matrices which are either the weights matrix or the Jacobian of the activation. You just keep sequentially tagging things on. Now if I've got any hidden layer, the Jacobian of the hidden layer is going to be if the activation applies individually on each component in a hidden layer, then the derivative for any component doesn't depend on the other component. So the Jacobian is going to be a diagonal matrix, right? Specifically, the diagonal entries are going to be the derivatives of the activations themselves. So the derivative of the activation functions, or the subgradient, is generally going to be bounded. And that's because the typical activation functions that we have never have infinite slope. They always have a finite slope, right? So those Jacobians f prime, they're going to be bounded, which means there's a limit on how much multiplying a vector by the Jacobian is going to scale it, right? Specifically, if I look at some of the popular activation functions, the red line is for which is this one of the, I don't remember which one it is. One of them is for ReLU, one of them is for tanh. But basically what we will find is that in the case of a ReLU, the slope is either going to be 1 or 0. Then you have the smooth versions of the ReLUs which go from 0 to 1. If you have a tanh, it goes from 0, then goes up to 1, then goes back down to 0. In every case, the derivative is upper bounded by 1, and then it's generally lesser than 1, right? So what does this mean? If I multiply something by this Jacobian, every component is going to shrink because the derivative is always lesser than 1, right? So which means that as we go back in the layers, when you're performing backprop, this is what happens when as you perform your computation going backwards. Actually, backprop is working its way out this way, but if you look at the computation from out to in, each of these terms is going to actually shrink the vector a little bit, right? Which means when I'm trying to compute the gradient is going to continuously shrink as I keep tagging more and more terms on towards the end. Now, which means that after just a few layers, each of these is going to shrink things. Everything is just going to vanish, right? Because if you have a sequence of shrinking operations tagged on one after the other, things will vanish. But then there's a second component, which are the weights matrices. And in a single layer recurrent network, for instance, the weight matrices are all going to be identical. So the chain product for the divergence is going to expand the divergence along the directions in which the singular values for the weight matrices are greater than 1, and it's going to shrink the divergence along the directions where the singular values are less than 1, which means that if you ignore the effect of the Jacobian, if you consider only the weights matrices, then any component that the divergence, initial divergence has in directions where the singular values of the weight matrices are greater than 1, they're going to keep expanding and expanding and expanding and rotating around till the whole thing goes up, right? On the other hand, if you look at the directions where the singular values are less than 1, it's going to keep shrinking and shrinking and shrinking and shrinking till the whole thing sort of disappears. So now in this case, for fixing, if you fix the Jacobian, the gradients are either going to blow up in some directions or they're going to shrink and become nothing. You have exploding or vanishing gradients, right? So now I have two components over here. Let me pair those two up. If I look at each pair of weights matrix and a Jacobian, then the overall behavior is going to behavior on the properties of these combined terms. So the chain product for the divergence of the final loss function with respect to the output of any layer is going to expand in directions where each stage, which is indicated by the underlined block over there, has singular values greater than 1, and it's going to shrink in directions where it has singular values less than 1, right? So I'm speaking of singular values rather than eigenvalues over here because we have different matrices multiplying these things. But now, what does this really mean? This means that as I keep going back, the gradients in the lower layer are going to sort of explode or vanish. Regardless of what the value here is, by the time I come over here, in some directions there will be no gradients left at all. In other directions, the things are going to generally blow up, right? And if I control my weight matrices such that none of their eigenvalues are greater than 1, then the thing is always going to shrink. And as you keep going backwards, you're going to keep combining these terms, and things are going to shrink. So, and the problem gets worse as the network depth increases because you get more and more of these terms. So here are some examples of of the kind of behavior we expect to see. This was for an MNIST model. This was, we have a 19-layer multi-layer perceptron. This is the output layer. That's the input layer. We are actually showing the log of the, we have 1024 units going left to right. And we are showing the log of the norm of the divergence of the error with respect to the weights of each unit at each layer, right? So the color over here basically shows you how large the gradient is for 1024 units over 19 layers. And this is an ELU activation. We're using batch gradients, meaning you're computing gradients on entire batches of inputs. And you see what happens. This is in the first iteration, right after you've initialized the model. And here's what the divergences look like. As you go to the first layer, there really is nothing left. There is no information left. Now what will happen, this is in the first iteration, right? At initialization. What do you expect will happen as I keep iterating and operating on the data? As I keep iterating and updating my models, the divergences are actually going to decrease because that is what gradient descent does, right? And this figure is going to get worse and worse. Now this is with ELU, where you can see some information all the way up to say here, after which becomes vanishingly small. This is with ReLUs. So this is with ELUs. We can see stuff going on for some distance. With ReLUs, things seem to vanish over here. With sigmoids, they vanish even earlier, right? And so you can see exactly how the gradients sort of disappear as you go backwards through the layers in the network. This is for a batch where I'm taking many inputs and computing things jointly over the entire lot. This is with TAN-H, same thing, right? Now if I look at individual instances as opposed to entire batches, and I look at ELU activations, again for individual instances, these are 9 of those, you can see that in every case, as I work my way the gradients back to the initial layers, the magnitude of the gradients kind of shrinks to almost nothing. These are again log magnitudes. So you can imagine that if I were not taking a log, they would basically be 0, right? They would all underflow. So ELU activations maintain gradients longest, but in all cases, gradients effectively vanish after about 10 layers. As you can see, 10 is around here. And as far as you can see, they're visually disappear. I mean, they're still making a difference in the sense that you have some stuff, yes. That's exactly what we talked about over here, right? In this case, the situation is if in the directions in which this guy has an eigenvalue greater than 1, right? Actually, singular values. Yeah, well, greater than 1, it's going to explode. In directions in which it's less, it's going to shrink. And what we have in this system is that there are no directions in which you have any eigenvalues which are greater than 1. So the things are always shrinking. Otherwise, you would see some components where you'd have the spike, and the rest of them are just going to disappear. Regardless, it's unstable, right? Things where you have a spike, it means that a tiny change of that parameter is going to completely destroy your output. And things where it goes to 0 means you can't really adjust your parameters because the gradient is 0. You don't know which way to go, both of which are bad things. But yes, they're two sides of the same coin, right? So and both batch gradients and the gradients for individual instances disappear. So it doesn't really matter whether you're doing stochastic gradient descent or batch gradient descent, the behavior is essentially the same, right? And in reality, they don't all disappear. A very tiny number may actually blow up depending on if some things align up with the weights, right? Now, so the problem is when you look at recurrent networks, the recurrent networks are really very deep networks. So if I'm operating on a long sequence of inputs, then the effect of some error out here on the gradients I compute out here is going to be 0. Simply because as you go through the layers, the derivative is going to become vanishingly small, right? So what this means is that although I nominally have a recurrent network and I say things are being remembered and what happens now is going to be affecting things way into the future, what really happens is that the network is really several blocks of short memory. It's actually behaving as many sequential blocks of short-term analysis rather than one long network with great memory. And this is something that we'd like to explore, something that we would like to avoid. So now secondly, stuff also gets forgotten during the forward pass. And why is that? Because we saw that if you're not using the tan H's, if you're using the sigmas, if you're using ReLUs, things are going to get saturated and it's effectively forgotten anyway. But even besides that, when I multiply stuff sequentially by the weights matrices, the same behavior that you expect to see going backwards is what you're going to see going forward. It doesn't matter whether you're post-multiplying or pre-multiplying by the weights matrix. The row or the column vector is going to shrink according to the eigenvalues, right? So stuff gets forgotten even during the forward pass. Whereas what we really have is we often have a need for long-term dependencies. So here's a little bit of text. Jane had a quick lunch in the bistro, then she, right? The fact that this was a she actually had to do with the fact that we used Jane and not John. And there could have been anything in between. It could have been arbitrarily long. So you had to remember stuff for a very long time. Remember the example where we were using the neural network to generate code? Now when I open a loop, I have no control over how long the program is going to be within the loop. But I do know that I must close the loop, right? So this means that I must remember stuff for effectively an arbitrary amount of time. And none of these structures that we are looking at have this behavior. Even if I use tabs, you're only ensuring, if I use tabs greater than 1, you're only ensuring memories for the length of the tab or some integral values, a small number of integral values of the length of the tab. It's not arbitrary. Things tend to either get forgotten or tend to blow up, right? And we need an alternate way of remembering stuff. And this is where we begin talking about long short-term memory neurons. I wish I could tell you that I understood all about these things. I don't know how many people there are in the world who completely comprehend how these things work. I am not one of them. But I can tell you the mechanics of it. So let's go through the mechanics of it. It's all mystery and magic, right? So here's what we really want. We have each of those blocks, And each of those blocks is going to shrink your gradient, right? I do not want it to shrink the gradient. So what we would, on the other hand, so what we really want is hopefully for things to be remembered, either going backwards when you're doing a backprop or going forwards when you're doing your forward pass. So if things must be remembered, then you really want behavior of this kind. At each time, you basically want, so right now what happens is that each of those guys is going to shrink by the sigma term, which has to do with the eigenvalues of the block. And you want that sigma term to become a constant. You basically just want the whole c times sigma to not expand or blow, or to not basically make things disappear or blow up. So we want a network that just remembers these things for arbitrarily long and to be recalled on demand. So this is where we introduce this notion called a constant error carousel, which is that you have a history that's going to be, as you're going forward, it's going to be passed through uncompressed. There are no weights, there are no nonlinearities. It's a linear operation. Nonlinearity shrink stuff. They cause things to be to saturate, right? Weights are bad things. They cause things to blow up. They cause things to disappear. So let's get rid of these. Let's hold something that actually, let's introduce a term that actually just holds the memory for as long as it's required to be held. Now, it's not enough to just hold things, because things keep happening, which means you can keep accumulating information over time. So we do need some way of forgetting things. We do need a way of modifying our memories, but then these must be controlled. These must behave. These must depend on what we have seen and not on a generic property of the network. Whereas in the way we've designed the recurrent network, whether the thing was going to be forgotten or whether the thing was going to blow up depended on the network and not on the input once it was triggered, right? So let's modify this and make it dependent on the input itself. So I have h of t, which is the history that's going to go through uncompressed. There are no weights, no nonlinearities, but then I'm going to have this scaling term that captures other triggers. So for example, I have seen Jane, so I have seen a female person, right? Or I've seen the opening of a loop. So I'm going to remember that a loop has been opened. When do I cease to remember that a loop has been opened? When I see the loop being closed. So I need some term which can tell it when to switch off, and that term depends on the input, right? So in other words, you're going to have a history term which keeps carrying information through till it's triggered into forgetting. And it's got to be triggered into forgetting based not again on the properties of the network, but based on what has happened on the inputs, right? So what we actually will have is this history. Well, I'm going to keep changing notation to stay consistent with the notation that people actually use. But then the history here is a nonlinear, is a linear thing. It's just carried through, which is occasionally modified by a multiplicative term, which depends on the input. But then we know that the network itself performs nonlinear operations. Without it, it's really not doing anything useful. So the actual nonlinear work is done by other portions of the network. You'd have this history component which is being carried through, and that history component is going to be used by some nonlinear operator on top, shown by the circles on top, which produces other stuff, maybe for the output of other layers. Now what the history remembers, whether it's going to be turned off or turned on, again depends on not just the input but also turned on history, right? So for example, if this guy says that I've seen the opening of a loop and the input says there's a closing of a loop, it's the combination of the two that tells me that the history must be turned off. So what we will have is that guy coming back into this along with the input to produce an output which says turn this guy off, right? So they have the nonlinear combination, which is a pattern detector which looks at what is currently being remembered and what is coming in to turn things off or turn things on. So you have the nonlinear operators which are independent of what is being remembered itself. Now this is the basic idea, but then now these things can get arbitrarily complex, right? So I can have other stuff coming in. Now whether I decide whether this history must be remembered or not depends not just on what happened, not just on what I've seen, other incidental things like what else am I remembering, right? What else have I seen? There can be other stuff coming in, which could be not just the output, but the history itself. Here what we had said was I operate on the history, something happens, that feeds back. I can just look straight back at the history, or a combination of the output and the history. Now all of this is information that we are passing to the pattern detector, which tells you whether the history must be maintained, whether it must be shrunk, whether it must be expanded. But again, it makes sense. In an intuitive way, it makes sense. It's convenient to think of this in terms of opening and closing in a code, right? You open a loop, you have to be very confident that it's time for me to stop remembering that the for has been opened because now it's closed, right? So this whole basic idea is what is captured in the so-called long short-term memory network, which explicitly latches information to prevent decay or blow up, and uses this to remember stuff. So instead of just letting exponential decay or exponential blow up, you introduce mechanisms whereby whether things are remembered or not depend on the input. But a primary characteristic of this is that it cannot be weighted in any exponential in any manner, because if it is, you have the problems with exponential blow up and delay, like a blow up or decay. You're not going to have direct nonlinear operators on it because that's going to cause saturation of various kinds. You're going to basically have a constant term which is just directly modified based on other things that you have seen, and everything is going to build up around this constant term, which we will call or this, it's not really a constant, but a memory term which doesn't have any direct nonlinearities operating on it, which we will call the constant error carousel, right? So what is the time, just to make sure? It's 10:04. So here's the standard recurrent neural network, which is they receive past recurrent outputs and the current input as in, so you have a hidden layer, you have the current input, both of them are going to go into some tan H, and you produce an output, right? That is, or produce the next hidden layer. This was your standard recurrent network, and H feeds to the output layer. Here you have something slightly different. This is what the actual structure looks like. The sigmas are multiplicative gates that decide if something is important or not. So this is what we spoke of. Something is being remembered. This guy decides whether the memory must be turned up or turned down. Then you have an additive component which says, must I be adding something to the memory? For example, I could be saying I've opened one loop. Now, hey, I've seen another loop, so let me increment the count of loops that I've got. So now it's up to 2 loops, right? 2 for loops, things of that kind. And again, remember that each of these things, these little dots, it's not just a scalar term, it's a vector. So what you would have is many of these components. Again, using my logic, maybe one of them is remembering for loops, another is remembering parentheses, the third is remembering square brackets. So you have different kinds of things being remembered, and each of them is going to have its own control. So the whole structure works across a vector, right? So the key component is the central portion, which is a remembered cell state. It's not what I represented by H. We will use it representing cell, C, and which stands for the constant error carousel. I'm not really sure where the terminology came from, but the idea is actually quite brilliant. And so here's what it's going to look like. You have the constant error carousel, which is this constant term which carries memory, as we mentioned, which is multiplied, which is modified multiplicatively by things which tell it when things must be shrunk or expanded, and additively by some triggers which decide whether the memory must be upgraded or not, right? You have things called gates, which are simple sigmoidal units with outputs in the range 0, 1, which control how much of the information is to be let through. So the first gate over here determines whether to carry over the history or to forget it, or more precisely, how much of the history to carry. So I've just noted that I've seen a for loop. Should I continue to remember that there was a for loop, or is it closed? So this gate has that property. We also call it the forget gate. We tell the system when to forget stuff. Now remember, note that we are actually distinguishing between the cell memory C and the state H that's coming over time. So we are distinguishing between memory and state. We are going to be using memory to compute state, right? Now the second gate has two parts, which has a perceptron layer that determines if there's something interesting in the input. Have I seen another for instance, right? And a gate which decides whether it's worth remembering. So this guy decides if there's something interesting in the input, and this guy basically decides whether it's worth my time remembering it. So for example, first component might say, I see something that looks like a loop, but really should I be incrementing the counter for square brackets, right? So and together they produce the output that actually gets added to the constant error carousel. So you have the first term, which is the forget gate, and this is the additive correction based on what you've currently seen. And now the output of the cell is this constant error carousel is the basic memory that is being remembered. That actually goes into, you typically compress it with a tan H, which takes a value between -1 and 1. This compression doesn't affect our ability to carry memory forward. Observe this. The memory is independent of the compression, and the tan H is what we really did was to pull the linear non-linearity off the memory and made it separate. And that compression is also going to be modified by an additional gate which decides if the memory contents are worth reporting into the state at the current time. So and while at it, now you can actually begin adding complexity to it, right? At some point intuition fails, party. So why not just let the cell directly influence the gates while at it? So which means that instead of having the hidden values affect the various gates, the memory itself can directly begin affecting the gates. All of this makes sense in the sense that the more information you bring to bear on deciding what must be remembered, what must be forgotten, whether an input is worth passing on, whether the hidden state is worth modifying, all of this, the more informed they are, the better the entire process is going to be. So here's what the overall operation is going to look like. You have some function of some activation sigma, all of the gates. You have the forget gate, you have the input gate, you have the output gate. The forget gate is what's affecting this guy. The input gate is what is affecting whether you have something new to remember. And you have the output gate, which is what is affecting whether what you're computing from the current memory is worth passing on. And each of these is simply a sigmoid because these gates are multiplicative terms, which take a value between 0 and 1, which operate on a weighted combination of all the inputs coming in, which includes the current cell value, current input, previous hidden values, and so on, and of course the bias, right? The details of the arithmetic you can just check up on the slides. So here's the complete LSTM unit. This is going to be the constant error carousel on the top. You have the forget gate, which decides whether what is being brought through must continue to be remembered. You have the input line with its input gate, which decides whether there's something new to add to the memory. And then you have the output, which is being computed from what is remembered, and then again gated by something which by a gate which decides whether this output is worth reporting or not. Right. Again, intuitively all of these make sense, and it's actually quite pretty. And now, so you can actually build each of these as a block which goes through time, which is a vector. There are several of these, and we saw this in the last class. Anytime I draw one of these, I'm actually going to have each of these represents an entire block. So you have the various gates, you have the various variables in the network. I won't go through the arithmetic. Take a look at this because we're going to have in standard format some questions in the quiz which have to deal with the arithmetic for these for LSTMs. So we'll refer you to a paper on LSTMs, the original paper. Please read it carefully, and we're going to have at least half a dozen questions just on LSTMs in the quiz. For those of you who are watching, keep this in mind. For those of you who are not watching, you're going to have trouble with 5 questions. All right. But then just shows how information from along various directions must be propagated back when you're computing the gradients, right? Which is quite crazy if you think about it. There are so many different ways to affect a single parameter that all of these must be accounted for when you're computing the gradients. Fortunately, the arithmetic actually derives very cleanly from these equations where we know exactly what the parameters are, and we can use the standard chain rule to compute your gradients. But if you look at the information flow, it's quite complex. Simply because we added the complexity, we made the network increasingly more complex by adding more and more controls to it in an attempt to figure out when something must be remembered, when something must be forgotten, when something must be operated upon, right? So final bit for today. So this is the flow of all of these things. I'm not explicitly deriving the derivatives, just left as an exercise, but you see how the information flow actually happens, right? Now, this recurrent unit, the way we defined the LSTM, it had many components which got to be fairly tedious and complex. So let's try to simplify the LSTM. Maybe it's a bit of an overkill. We don't need so many components to it. So here was the LSTM again. Was it? We have a forget and an input gate. Let's combine the two. If the new input is to be remembered, that means that the old memory is to be forgotten, right? So why should I was saying that we had two components. The first one said, if I opened a loop, let me forget it. There was a second component which said, if I've seen a new loop, let me increment it. They're not two independent operations, right? Either I'm closing a loop or I'm incrementing the count of loops. I don't need two separate things to be happening on one trigger. So we can combine the two, right? And so that gives you this little gate over here, which is a combination of the input gates and the forget gates. Similarly, there's no need to bother to separately maintain compressed and regular memories. What we said earlier was that we had the regular memory C, then we had the H, which was obtained by compressing C. I mean, do you really need two of these guys? Not really, right? It seems to be like an unnecessary storage of stuff and maybe too many adding parameters. So let's just retain only the memory, but compress it before using it to decide on the usefulness of the current input. And that gives us this modified model, which is called the gated recurrent unit, which I have to the right, equations to the right. The GRU, it's a term that you might encounter, is just a simplified version of the LSTM which gets rid of some of the redundancies without actually losing information. So I'm on time. So I have the LSTM equations over here. This is only for your reference. Take a look. The basic idea that I was trying to convey during this lecture was how the whole idea could be built up. And that is the key piece. The actual implementation of the equation is not something I'm going to be able to convey to you in class and that you will remember. That is something that you will have to go through on paper by yourself when you're implementing these things. So here's a typical architecture with LSTMs. Each green box is now an entire LSTM or GRU unit, and you can have multi-layer networks. You can have bidirectional networks, which is exactly the same as bidirectional recurrent neural networks, except now the units are LSTM or GRU units. And the learning rules are also going to be, follow the same kind of mechanism that we had for the RNNs. One issue that I've left out is how exactly do you define the divergence. In the next class, I'm going to be talking about the divergence, but I'm not going to be making a distinction between recurrent neural networks and LSTMs. For the most bit, nobody really uses RNNs anymore. You use LSTM simply because they have this ability to latch on to things and decide whether things must be remembered or not based on the input rather than as an integral property of the network itself, which is a behavior that we are finally actually looking for, right? So I'll stop over here and take any questions for a minute. Otherwise, we'll continue in the next class. Yes?
So for the LSTM, why the value doesn't go up or vanish? Because you simply add
the memory in principle. So you're just there is no weight, right? So which means you don't have a multiplicative term which can be greater than 1 and keep exploding things. So now the contribution is additive. And because it's additive, it could blow up, but you'd have to wait for a very long time for something to become 10 raised to 20, right?
Forget gate, you can, I mean,
The forget gate is always shrinking it, so yes.
but you can get a vanishing issue.
But that, again, that depends on the input. My point being, things are not blowing up or forgotten based on the properties of the network. They are based on what you see in the input, and that is behavior that you want, right? Whereas in the standard structure, if I just change my weights a bit, things would blow up or things would shrink, and that's what we didn't want, right? Anybody else on the streams? No? Thank you. Perfect.